Integration Roadmap Committee. I'm here to introduce the Heterogeneous Integration Roadmap and also to explain why we participate in the ODSA initiative. 55 years after Moore's Law, the world has changed significantly. CMOS scaling is no longer driving the pace of progress, and ITRS, the International Technology Roadmap for Semiconductors, is over, and the world is evolving in ways never imagined before. We are entering a period of technology chaos driven by new ideas and increase the pace of innovation. New ideas such as ODSA. Heterogeneous Integration Roadmap is founded with initiative from 3 IEEE societies: Electronic Packaging Society, Electronic Devices Society, Photonics Society, SEMI, and American Society for Mechanical Engineers, Electronics and Photonics Packaging Division. Our purpose is to maintain the pace of progress needed for electronic systems today and tomorrow by integration of separately manufactured components into a high-level assembly that provide enhanced functionality and improved operational characteristics. Here is a pictorial representation of heterogeneous integration. Heterogeneous integration by materials, component types, circuit types, nodes, bounding, interconnect method, and different sources. We can have die from Fab 1, from Fab 2, Fab 3, different nodes, MEMS, and sensors, all incorporated into a system in package. So now we see a slide from Bobby Benanokoda at the Heterogeneous Integration Roadmap this year. He showed the ODSA charter, which is an open device-to-device interface, reference designs, reference workflows with the purpose of integrating the best-in-class chiplets from multiple vendors into a single function package so that it can go to the marketplace. This is very much similar to what the vision of Heterogeneous Integration Roadmap. The Heterogeneous Integration Roadmap has 21 technical working groups, 6 on market applications, and 5 on heterogeneous integration components, 6 cross-cutting topics, 3 integration processes, and design, co-design, and simulation. That will be 21 technical working groups, and if we separate co-design and simulation to be 2 different chapters, then we have altogether 22 chapters. The Heterogeneous Integration Roadmap was launched in October 10th last year. Let me read off a portion of the press release. 2019 release of the Heterogeneous Integration Roadmap, a roadmap for the future of the electronics, identify technology requirements and potential solutions. The primary objective is to stimulate pre-competitive collaboration among industry, academia, and government to accelerate progress. This roadmap offers the professionals, industry, academia, and research institutes a comprehensive strategy forecast of technology over the next 15 years. So you might download your personal copy of the Heterogeneous Integration Roadmap, the 2019 edition, at the IEEE Electronic Packaging Society website, composed of 22 chapters and 562 pages. Here is a way to download your personal copy of the roadmap chapters. The International Technology Roadmap Committee is composed of representatives from the 5 sponsoring organizations. We work together with hundreds of volunteers from across the world to put together this roadmap. Finally, the roadmap 2019 edition was released October the 10th last year. The 2020 edition is work and ongoing, planning for September 2020. We welcome collaboration with ODSA, and we invite you all to download the roadmap. Thank you very much.
Hello, welcome to OCP Global Summit. My name is Manoj Roge, and I am VP of Product Management at Acronix. I'm going to talk about my past experience with heterogeneous integration and future trends. Let me walk you down the memory lane. Memory vendors led heterogeneous integration about 2 decades ago. When I was at Cypress 20 years ago, I ran known good die business where we shipped low power SRAMs to flash vendors who integrated SRAMs and flash memories in same package. You can see that on the roadmap slide and the E Times article to the left. This was done like back in 2000. Many technical and commercial issues were sorted out then, and they can be in future too. Back then, standardization helped too. JEDEC standardized the pad layout, and memory vendors developed known good die and wafer level burn-in test flows. And these weren't just research projects, they were used in high volume too. For example, Motorola Razr phone shipped in 2003 had these memory stacks. So why chiplets now? First, as Moore's law is slowing down, heterogeneous integration is the way to deliver more than more. These are some of the recent product announcements of how some of the major companies are adopting chiplet approach for building next generation products. For example, AMD, Intel, Nvidia, Xilinx, and a few others have integrated HBM memories with their logic die. DARPA announced CHIPS program to drive heterogeneous integration. But the current challenge is it's a closed ecosystem, which is not good for anyone. But now OCP is driving open chiplet architecture. Secondly, chiplet ecosystem is starting to emerge with multiple low cost, low power options for PHY, for example XSR SerDes or HBM like parallel interface. PHY agnostic protocols are emerging such as CXL, and standards based chiplet options are becoming available. We at Acronix have chiplet as part of our roadmap that I'll show in a couple of slides. But first, let's step back and look at what's going on at a system level. If you look at the legacy data centers, they were all built around CPU. But CPUs can't keep up with rate of moving and processing data. The hyperscalers are building infrastructure to move data management off of CPUs because CPU cycles are valuable and shouldn't be used for moving bits. Hence you see smart NICs being deployed in data center. The other challenge for hyperscalers is some of them have their own custom requirements, hence they need programmability in both networking and compute workloads. Furthermore, for compute workloads such as AI machine learning, the machine learning networks are evolving rapidly. And in general, it's just difficult for infrastructure manager to predict what new workloads would look like. This is where FPGAs that can adapt to evolving workloads and future-proof data center infrastructure and offer higher performance and better TCO come into play. So these are some of the FPGA chiplet use cases we see. For smart NICs, one can combine FPGA for hardware programmability with NIC ASIC and a CPU chiplet. We see strong interest in combining best-in-class ADC DACs, which by the way can be built in process optimized for analog, with the FPGA chiplet in the most advanced logic process such as 7 nanometer TSMC. For many years, FPGAs offloaded complexity of memory interfaces and emerging Ethernet standards so that networking OEMs could build their data path ASICs such as the one shown there, the 400 gig packet processor and traffic management ASIC. And we see the same happening with AI ASICs now, where They can offload the complexity of 400 gig Ethernet, PCIe Gen 5, HBM memories, and so on. So this is a one slide summary of our product offerings. Acronix is the only FPGA vendor that offers all three form factors. Number one, standalone FPGAs like you get from Intel and Xilinx. Number two, we license the FPGA IP to be embedded in customers' SoC. And number three, we have plans to build standard chiplets as we get industry to align on standard parallel or serial interconnect. And in the meantime, we are working with customers on building custom chiplets. So in summary, we are very excited about the open chiplet architectures and heterogeneous integration, and we look for collaboration with many companies that are part of this effort at OCP.
Hi, my name is Shyam Chandra. I'm the security protocol architect at Lattice Semiconductor. Today we'll talk about the role of control, management, and security in a system in a package or a SIP. So one of the challenges of adoption of a SIP in a system is how well we are able to adapt or modify or make it backward compatible of these functions like control, management, and security. For example, if you take the standard SIP specific control path, you need to implement power sequencing, reset sequencing, telemetry, or it's glue logic connecting between the two the chiplets. These are not standard. They are chiplet dependent. So a chiplet should be able to provide on the one side a interface with the non-standard signals, and on the other side, these SIP's front end, a standardized control path, and that will simplify the implementation. For example, implementing MCTP protocol. A SIP should also control its own power sequencing of supplies on the board. So the circuit board, it's very easy to design the circuit board. They just supply the power. The sequencing is handled by the SIP itself. Sometimes it has to even manage the partially owned, partially powered conditions for extended period of time to protect these chiplets. Now, the other aspect is if the chiplet has to be used in a board, it is much easier if it can interface with the incumbent infrastructure, backward compatibility of the control protocol and logic. A chiplet's protection in a supply chain, today in this world, people are talking about security of any system in a supply chain. It can be protected against attacks in manufacturing or in transit or in system integration and so on. So we need to be able to make key provisioning or provide traceability, attestation, all these functions that are relevant to security to be easy to implement. And also, you want to make sure that you log all the touch points and be a root of trust for reporting. And it's not enough if we make all these functions. These chiplets will have all the accelerators and so on. They have their own firmware, but the control functions also should be able to be updated in the field so that you have future proofing. You might want to update the control algorithm. So if we address all these challenges, we will accelerate the adoption of a SIP. Let us look at a block diagram of a chiplet, of a system in a package. Usually you have a CPU, a network interface chiplet, maybe a domain acceleration chiplet, and CPU is booting from its own firmware, network interface chiplet booting from its own firmware. And here in the center, we have a secure control and management chiplet. And this is the Lattice's chiplet that is based on Lattice's Nexus platform. What this device does is it uses its on-chip Fpga and the on-chip ADC to perform reset and power supply sequencing functions. The RISC-V processor on chip also is used to orchestrate platform firmware resiliency that is NIST 800-193 compliant. It is also able to communicate, implement secure out-of-band communication with not only the other chiplets on the board, but also with the main board. And this could be MCTP compliant. And this device can act like a symbiont root of trust to the main root of trust in the main board. So this can act like a full-fledged root of trust, or it could be a symbiont root of trust for the entire system. The other functions here that you can implement in this is something like a NCSI interface. Is this network controller's side channel interface for NIC 3.1 and beyond. It could also have a source synchronous interface that communicates with the CPU at very high speed, like 1.5 gigahertz. It could also offer a PCIe channel, and this could offer MCTP or PCIe functions. We also have D-PHY interfaces, so it could also drive video camera if the function requires. The logic inside the fabric is also optimized for implementing AI-based prediction functions. Like, for example, if you want to monitor solid-state storage performance, monitor its delays in response, or look at the board supplies, recovery and turn off, turn on functionalities, and predict its failures. So we could add those things as well. So we can make the whole system either simple or fairly complex and sophisticated. So here we have the Lattice chiplet that does all the power sequencing. We have a chiplet, like say it's a processors, SoC or FPGA, and there is a SPI switch, and these boot from a SPI quick switch. And the Lattice device, chiplet, secure control and management device would authenticate the information, the firmware stored in there, so what we call real-time detection, or it can, if the contents of the SPI memory failed authentication, it could help recovery from a different location, or it could recover from a securely stored SPI memory. And this is real-time recovery. And it can also offer real-time protection, that if malicious code gets a malicious container, turns on in the processor code and starts to attack the SPI memory, this would be monitoring the SPI bus real time and capture those malicious commands and block them from affecting the SPI flash. So this is real-time protection as well. So this is what we call dynamic trust. So this makes the whole system remain pristine all through its lifetime, and manage also the in-system updates. So it'll still allow the in-system updates to the SPI flash to go on, but only authorized updates. Lattice has developed a PC chiplet, or what we call the pitchlet, for secure control and management functionalities. This is fully functional and is available for you to build your own proof of concept system in a package. We have full software support for this device, and please contact Shyam Chandra if you need any assistance in this. Thank you.
Hi there, I'm Sam Fuller with NXP Semiconductor, and I'm happy to speak at this virtual OCP Global Summit. I'm here to talk about a project within the Open Domain Specific Architecture, the ODSA workgroup within the Open Compute project, focused on die-to-die technology. And in particular, I'd like to talk about the die port technology that NXP has contributed in the form of a specification to the ODSA. Die port is designed to solve a specific problem, and that is the challenge of scaling a chip design across multiple devices in a simple, easy way. One of the big challenges is that for the IP that is typically used to develop modern semiconductors, there are no standard mechanisms established to allow a system architecture to easily spread across one or more devices or die within a package. You could leverage technology like a PCI Express or even Ethernet or some sort of a standard bus technology, but in particular in the chiplet-based design methodologies, there are specific approaches to the physical layer interconnect between devices, and those approaches will leverage either very wide buses or very serialized interfaces. And either of those approaches, there's just no established standard for how information from one die should be sent to another die, and that's the problem that die port is trying to solve. So this diagram kind of shows this, in that you have kind of an I/O coherent interconnect between two devices. There's a AXI, which is a well-standardized on-chip bus interface. And much of what die port does is it allows the AXI and other signals to be sent across a standard interface such that it can be completely replicated on two die, so that the device sees technology on the second die as if it were on the same die. And that obviously simplifies a lot of system and software design if you can have a technology that does that. So the goals of this technology are really to optimize the die-to-die communication. This is designed around a virtual interconnect of AXI buses, and it's been optimized for latency. The speed at which those transfers take place is important, the bandwidth, the amount of data that can be sent in a given amount of time, as well as trying to minimize power and cost, which are always important in the semiconductor industry. As I mentioned, the connected die appears to software as an on-die resource. So critical system information and messages, kind of state of the system, are automatically shared across the die, and so the information that is needed on a second die, it will be there as if it were on the same die. It is optimized and designed around the standardized AXI protocol. It is expandable for ACE Lite or ACE support, which is a little more enhanced version of AXI. And it provides that kind of hardware linking and synchronization of the AXI bus channel between the die. This technology is also designed with an eye towards building reliable and robust systems. So things like error detection and prevention and functional safety are also comprehended in the design. That includes robust test support and kind of startup, reset, frequency changing, and error management for the system in package devices. Sometimes these technologies will get developed and they won't have anticipated the need for example, error correction, or detection across that interface, and then that technology really just can't be leveraged in a lot of critical safety applications in automotive or aerospace or industrial type applications. There's also a goal, although not in the initial specification, around a plug-and-play support, although our perspective is that in these die-to-die type applications, there isn't typically going to be a need to discover what's connected on the other side kind of at power up that can actually be built into the system. This is a high-level block diagram of the interface. You can see that it supports both this AXI master and slave port, and so there are essentially two ports, master and slave on both sides. Like a master can be a slave to another device, slave can be a master to a device, and then there are input and output internal signaling mechanisms that allow signals beyond the AXI bus to be transited as well. Then there are a set of machines that kind of convert the data that's coming from the wide buses and stages those to a link layer that serializes the communication into more of a packet-based format, and those are sent serially across a serial diport bus that could be multiple lanes. And there's a physical interface there. So that's the approach that is taken here. And just as as we wrap this up, there are a variety of message types. In the AXI domain, there are writes and read type applications, write and read type transactions of various data links, and those messages can be packed such that you can do back-to-back messages, and you've got responses that allow for very tight packing of data across the interface. Beyond the AXI messages, there are also signaling messages that can be sent, and you can signal reads and writes. Those could be things like specific signals that you want to transport across the bus, and those can be defined in the standard. Okay, so anyway, this is development work going on within the ODSA. It will be an open standard. Members of the ODSA group can both participate in reviewing as well as contributing to the standard. We'd like everybody to get a chance to use this, and welcome the participation of the industry in the development of this important technology.
Good afternoon. My name is Elko Bergman, and I'm Senior Director of Business Development with ASE Group. ASE has been participating in the ODSA since last fall, and over the past several months have identified opportunities to collaborate with and add value to the ODSA effort. Today, I'd like to briefly introduce you to our company, our service offering, and the enabling solutions we offer for heterogeneous integration. Then I'll share with you what's driving our interest in participating in the ODSA project and how we believe we can support the development of a robust chiplet ecosystem. For those of you who are not familiar with ASE, ASE is the world's leading IC packaging and test manufacturing services provider. We are part of ASE Technology Holding, together with our affiliate SPIL, also providing IC packaging and test services, and USI, our electronic system manufacturing service entity. Combined, ASE Technology Holding reported a consolidated revenue of $13.5 billion last year, of which $8.1 billion resulted from our packaging and test operations, and the remaining $5.4 billion from our EMS/DMS activities. We employ over 100,000 people and have our primary manufacturing facilities in Taiwan, but also operate in other locations throughout Asia, including China, Korea, Japan, Malaysia, and Singapore, and in the case of USI, also in Europe and North America. As you can see, to support the semiconductor and electronics industry, ASE provides a complete suite of services across the value chain, with the exception of semiconductor design and wafer manufacturing. Starting on the left side of the chart, to support the early stages of design and development, we offer engineering services through our ISE Labs facility here in Fremont, including test software development, device verification, qualification, and FA services. Then, post-wafer fabrication, our IC packaging capabilities include wafer sort, bumping, package development, design and assembly, as well as component final test. In addition, we also provide system-in-package, high-density module development, integration, manufacturing and test services, and final system PCBA assembly, system-level test, and logistics management services through a combination of ASE's and USI's capabilities. We are the only global microelectronics manufacturing services company that has successfully integrated OSAT and EMS businesses to deliver a unique and complete value chain solution. ASE clearly sees and recognizes the industry drive towards die partitioning and the integration of heterogeneous silicon into virtual SoCs. This trend is driven by a variety of factors, including silicon cost and yield improvement, IP reuse, process node and performance optimization, separation of digital and analog functionality, and the continued need for increased performance and bandwidth, particularly as the IC developers continue to move to larger die sizes and more advanced process nodes. To address this industry direction, ASE offers a range of advanced interconnect solutions for silicon integration, starting from PCB substrate-based SiP modules for wearable IoT and other consumer applications, and then moving towards the right with increasingly higher density interconnect solutions, including flip chip multi-chip modules to support multi-die integrations such as SoC with SerDes, high-density fan-out interconnect for large die partition and high-bandwidth memory integration, requiring tens of thousands of die-to-die connections, and all the way up to silicon-based 2.5D and 3D integration platforms, leveraging sub-micron line space routing capability. Needless to say, all of these heterogeneously integrated package solutions require significant design and simulation support that would normally occur during the SoC design process. And this brings me to ASE's interest in the activities of the ODSA. ASE clearly acknowledges the significant thrust towards heterogeneously integrated solutions and has been making significant investments in package technology development and advanced manufacturing tools and capabilities to support this direction. One of the keys to success in achieving widespread adoption is the development and enablement of a complete ecosystem across the value chain that will simplify the design and integration process. The ODSA's effort in developing physical and logical interface standards is a significant step towards that objective. However, as the industry moves to partition virtual SoCs, a portion of the interconnect design complexity that was previously dealt with at the chip level is now moved into the package. In our view, in order to avoid complex, custom and extended package design and simulation cycles, there's an opportunity to explore the development of interface layout standards, design rules, and guidelines to facilitate this process. This is not dissimilar to the types of standards that already exist for interfaces like DDR or HBM, but we would like to see if this approach can be extended to BOE, OpenHBI, AIB, and other emerging chiplet interfaces. The objective being to facilitate an open source chiplet ecosystem capable of supporting the rapid integration of multi-source and process technology chiplets, utilizing these interfaces to promote mass adoption of this new paradigm in the IC design methodology. For next steps, we propose the establishment of a cross-functional working group consisting of chip interface architects, EDA and library suppliers, and package substrate design and simulation service providers. The objective for this team would be to look at the feasibility of developing the standards and specifications for pin layouts and assignments on an interface like BOE, and then define the associated design and performance guidelines for the routing of such an interface between two chiplets across a package on a variety of interconnect substrates, including organic substrates, high-density redistribution layers, and silicon-based interposers. Once the design guidelines are established, reference designs can be created, and together with the design rules be considered for implementation into the design tools commonly used for chip package co-design. The validation of this approach could be the demonstration of a virtual chiplet integration flow together with ODSA. We welcome your feedback on the viability of this idea and would appreciate your participation and support. Thank you for this opportunity. Please don't hesitate to contact the ODSA or myself with any questions or suggestions.
Hello, my name is Manuel Mota and I am Marketing Manager at Synopsys. Synopsys is collaborating with ODSA to help achieve the common goal of enabling the data center ecosystem with key IP technologies and technical expertise. We are participating in several ODSA sub-projects, including OpenHBI, PHY, and BOW. With nearly 30 years of leadership and technical expertise in the interface IP, including PHYs and controllers, Synopsys enables the ecosystem with silicon-proven high-quality IP that is most trusted by our users and widely integrated into the most complex SoCs in the most advanced FinFET processes. Our users have been able to deliver a vast number of successful SoCs while accelerating their time to design and reducing integration risks. Our DesignWare IP complies with the most widely used protocols in data center, edge computing, and network SoCs. The protocols include 112 gig Ethernet, USR, XSR, HBI, PCIe 5.0, DDR5, HBM2 and 2E, C6, CXL, as well as multi-protocol PHYs. The Synopsys die-to-die IP enables the shift towards die disaggregation and chiplets with standards-compliant die-to-die PHYs based on 112 gig USR XSR SerDes architecture and parallel HBI architecture, all optimized to support various packaging technology options, from organic substrates to silicon interposers. Synopsys die-to-die PHYs deliver leading power, performance, area, and latency, while enabling reliable connections with low bit error rate between two dies. They are configurable solutions for very high bandwidth efficiency per bit front millimeter, supporting a wide range of data rates up to 112 gig per lane. Synopsys is unique in that it provides signal integrity and power integrity analysis of the channel design and validation within the package, all to make the IP integration easier. In addition, our die-to-die PHYs are compliant with OIF CAE 112G and CAE 56G standards for USR and XSR links, are compliant with AIB and HBI standards for high-density parallel interfaces. They are area optimized, enabling maximum placement flexibility in the die periphery. They are self-contained, protocol agnostic, implementing all calibration and adaptation and other advanced algorithms for robust operation over VT. They implement built-in loopbacks, testability and diagnostic features to provide increased testability and coverage. Their low latency data path architectures are ideal for connecting disaggregated dies in MCMs for servers and IE applications. Synopsys is an active participant in the ODSA sub-projects and works with all the members to help promote the standardization efforts of the Open Compute Project, or OCP, with high-quality interface IP that designers can use to overcome their design challenges and accelerate time to market.
Hi, everyone. I'll give you a quick update on Chiplet Design Exchange workstream. My name is Jawad Nasrallah. I'm CTO of ZGlue. In this workstream, we primarily focus on three things. First, we are looking into chiplet description formats. And we started out with physical modeling. More recently, we have been working on power modeling that will eventually lead to thermal modeling of chiplet-based integrated circuits. The second thing that we have been working on is proof of concept system in package design flow and associated aspects that connect with the proof of concept PCB work that is in progress in the POC work stream. And the key thing here is to come up with design flows under the CDX umbrella to take all the collaterals that are being developed in the POC work stream and can use that to build a SIP multi-chip module. Thirdly, we had previously been working on a chiplet catalog, and there are a couple of incarnations that have been realized, and one of them is the chiplet store. For the power modeling work, we have adopted a test case in the CDX workgroup as shown in this slide, which is a SIP system that ZGlue has put forward for the participants to develop the power modeling and associated description formats. So if you participate in the CDX workgroup, you will see that we are working on a chiplet power description mechanism. This power description mechanism, the idea is to take the data sheet of a chiplet and extract all the power related information and put it into a machine readable format. So on the left side, you are seeing the system, the test case that I just mentioned. For each one of the chiplets in the system, we intend to have the description as well as a power scenario and different modes of operation, along with normalization information. All the power has to be normalized to same value of VDD and temperature, etc. Additionally, there has to be a netlist that gives you an idea about how things are connected and what are the parasitics. So with the architectural information that essentially defines connectivity and power vectors, we plan to take all of the power description coming from these data sheets and convert that into a power calculator format. And the ones that we are right now working on, one of them is UPM, which is an IEEE format. And the CAD tool that we are using in this particular case is Power Meter from Trace Systems. Secondly, we are now starting to work on a SIP flow to take the proof of concept P chiplet based system and make a SIP with it. Now, in this particular case, the idea is that we have all these pitchlets, which are being built in a PCB format. We know their bill of material, their netlist, schematics, and floor plan. And we also have the baseboard, where we have pretty good idea about the schematic, netlist, and connectivity of different pitchlets. We combine that with various constraints, such as the power thermal footprint and compliance and design rules and design for manufacturability rules. And we'll come up with a recommended design flow, which will essentially be used to take this information and build a SIP with that. Now, this is one of the key areas of activity in CDX workgroup right now. Lastly, I'd like to mention that there is a catalog that is available through ZGlue. This particular catalog has about 2,200 chiplets available. They are in the ZEF format, which is the ZGlue open source format, but all of this data can be converted to pretty much any design tool out there. And the number of chiplets available under this platform are increasing on a continuous basis. With that, I'd like to invite folks to come join Chiplet Design Exchange. We are looking for participation from EDA, OSAT, design services, chiplet vendors, and even distributors to come and join. They help us define the chiplet packaging design flows, list your chiplets, share your requirements, and your wish list for chiplet modeling. With that, thank you so much.
Hello, my name is Vladimir Stojanovic, and I'm a chief architect in IR Labs. I would like to introduce a monolithic in-package optical or MIPO I/O chiplet that IR Labs have developed. The chiplet is named Terafy and is meant to provide optical I/O connectivity off-package to a range of host systems on chip integrated together with the chiplets in a multi-chip package environment. The unique feature of the technology is a monolithic integration of advanced CMOS transistors with silicon photonics that enables the optical I/O function. This monolithic integration is key to enabling co-packaging in existing multi-chip package ecosystems like organic substrates, as well as 2.5D integration with a range of approaches, starting from Intel-specific embedded interconnect bridge technology to silicon interposer CoWoS style techniques, as even high-density build-up fan-out substrates. On the right side, we're showing an example of this integration where, through collaboration with Intel, we have assembled a multi-chip package based on EMIB technology, where we have co-packaged 2 Terafy tiles together with an Intel Stratix 10 SoC, as well as an Ethernet CMOS tile. Some of the Terafy chiplet specifications are shown below. We plan to start sampling these chiplets in the second half of 2020. The chiplets have up to 4 terabits per second full duplex bandwidth, consisting of 2 terabits per second transmit, 2 terabits per second receive, sliced over a total of 64 optical SerDes lanes, and partitioned in 8 optical macros, each supporting 8 wavelength division multiplexing on a fiber. The chiplet operates at less than 5 picojoules per bit energy efficiency per link, as well as 540 gigabits per second per millimeter. The energy number is inclusive of the external laser, which is located outside of the MCP package. Chiplet also supports an AIB 1.0 interface toward the host SoC. It's compatible with the AIB interface already existing on the Stratix SoC, as well as with the specification that is opened up for access through the CHIPS Alliance. Regarding the scaling roadmap, the technology has the capability to scale up to over 20 terabits per second per chiplet at energy levels of 1 to 2 picojoules per bit and densities in excess of 2 terabits per second per millimeter by increasing the data rate per wavelength and number of wavelengths per fiber that can be supported. We're also looking forward to implementing more advanced AIB interface 2.0, as well as a range of other electrical interfaces like AHB 3.0, USR, XSR, as well as potentially a bunch of wires and MDIO interfaces. Thank you.
Okay, my name is Brian Allison, and I'm from IBM. And today's lightning talk will be about exploiting composable heterogeneity through open architectures. So today's talk, we're going to go over some of the chiplet design opportunities that we're looking at over here at IBM. The first couple of discussion points will be around chip disaggregation, as far as cost reductions, modularity, latency reductions, and then we'll go through some system integration thought processes that we're having around more efficient connectivity, system densities, and some integration. So what we're going to go through right now is just talk about some of the potential package level modularity things. What we've done here is broken down a large monolithic die into the various subcomponents, whether they be the core and the caching structures, the PCI Express I/O connectivity, accelerators, memory controllers, the local fabric bus, things of that nature. So each one of those, if you think about that from a chiplet perspective, they are all decomposable. And if you can actually design your monolithic chip and break it down into subcomponents, you can actually modularize this whole thing and make it into a chiplet infrastructure. Now, what ends up happening is that the IP providers can deliver, let's call it tested physical chiplets, right? And so it becomes a lot more cost effective to do this at a chiplet-based form factor than doing large monolithic dies. And you're seeing a lot of this out in the industry today by a lot of the industry leaders doing processor design. That avoids a lot of time-consuming and expensive reintegration when you do things into an SoC. And then what you can do is you can design durable IP blocks that don't necessarily have to change. So in other words, if you design something that's like an I/O infrastructure, you can make that composable into multi-generations of processor designs. So you can see that as I forward through these slides, you can do things like this as far as memory controllers, memory interfaces, power bus infrastructures, or fabric infrastructures, whether it be an I/O infrastructure like PCI Express, and then even a core L3 structure. Now, some of the benefits of actually doing a chiplet type integration is some of the latency optimizations that go behind that. If you do something like a very large monolithic die, the transport delay going from, let's say, one L2 core to a DDR memory controller interface might be greater than 3 nanoseconds of transport delay. But if you're to do that same type of crossing, but on a chiplet-based design, you actually get a lot more efficient transport delay. So what we've been doing, or what we've been observing when we do our signal integrity and our analysis, that we're actually seeing that modular wiring offers a greater than 10x advantage in time of flight over just the best of on-chip transport. Now let's go over some of the chiplet design opportunities. These next set of slides, we're going to talk a little bit about heterogeneous integration. One thing that we think is very relevant with this type of integration is that chiplets, they deliver value in a couple of different facets. It is the right compute for a number of different jobs. You can actually have diverse technologies to maintain system balance. Not every single chiplet actually has to be the same process node. You can actually carry things forward, like let's say you have a 14 nanometer I/O subsystem. You could carry that forward into different processor nodes, for instance, based on a chiplet-based MCM. You can do extreme connectivity through advanced packaging. So I think you're going to see a lot of focus areas around advanced packaging these days. And then it's a lot simpler, the demands of delivering IP chiplets than delivering a full SoC. Now, some of the chiplet challenges and requirements that we see going on in the industry today, it does require a broad range of packaging innovation. So when you're delivering these large MCMs with all of these chiplets, right, there is a lot of packaging innovation as part of that overall solution. You have to have open PHYs and protocol standards, so you can have all these chiplets connect together, right? Because you don't want to have proprietary interfaces connecting these chiplets. You got to make sure that you're doing them through open standards. Cooling and current delivery is a challenge. Robust test infrastructures. This is a totally different paradigm these days as far as how you test all these chiplets. Standards and tooling. So the toolings that you typically would use through, let's say a Synopsys or a Cadence or something like that, those are changing to handle these chiplet architectures. And then you have to have an ecosystem to take advantage of all these chiplets. Now, one of the things that IBM's been working on over the last 3 to 4 years is an architecture that is open and architecture agnostic, so we believe it fits very nicely in the chiplet paradigm. It is asymmetric, it is latency optimized, it's very flexible, it can do a lot of different things. It can do accelerator attach, it can do coherent network controller attach, it can do advanced memories, it can do standard memories. It's very flexible, it's very robust. We've actually got a very good ecosystem around OpenCAPI 3.0 and OMI, so we believe it fits very well in the chiplet realm these days. Now, some of the things that we're seeing with some of these open standards for servers, right? The ability to disaggregate the chiplets into customized form factors, right? Whether it's the CPU socket, whether it's a memory DDIMM, whether it's the I/O subsystem built around PCI Express, whether you're doing a memory subsystem around OMI, whether you're using open accelerator mezzanine to do the attachment, right? To decompose the server into these different components also lends itself to, let's call it a chiplet-based paradigm. Now, if you look at the power-based family of processors that we have today, we actually do have a memory architecture called the Open Memory Interface, where we do have an architecture agnostic bus for memory attach. It can be used for storage class memory. It can be used for memory buffers. So what it means is that through a single memory buffer, you can actually have different types of memory architectures behind memory buffers. So instead of actually having to respin your processor silicon to take advantage of these new memory technologies, you can design memory buffers or something of that nature to evolve with the memory architectures and technologies as they forward migrate in time. And so why that's relevant is that you can get some extreme bandwidth, low latency, low cost. You get enterprise type RAS capacity and bandwidth, and then you can actually start to follow all of the storage class memory type environments and use this architecture called OMI to address the emerging memory technologies that are coming into the marketplace today. Today, there is a company out there called Microchip that actually did the first OMI implementation around this open architecture. So they actually are bringing into the marketplace today something called a SMC 1000. It is an OMI-based DDIMM solution. It is a JEDEC standard. It's got a very good load-to-use latency characteristics. It does support a 25 gig signaling rate. So what it does is, for every I/O of processor pin, you basically get 4x the raw bandwidth over doing traditional DDR. And we believe this type of architecture is where open architectures and protocols really want to go, because you get media independence, you get low solution costs, and then you get increased memory bandwidth when you do this type of development. So if you look at the overall OpenCAPI design goals, like I mentioned earlier, support a wide range of devices. It is ISA independent of host architecture. It does support a plurality of devices. It is a trusted type architecture. It does supply cache coherence. And so, if we look at things that a chiplet-based design, and then a chiplet-based open architecture, we believe that it's very well suited towards that type of paradigm. Now, if we take a step back, we talked about a number of different things in this talk. We talked about the disaggregated trends that are going on as far as rack scale, breaking apart all these separate components into different pools, whether they be memory, CPU, GPU, storage. We do have a common interface goal. We understand that there are chiplet trends going on in the industry. And then we actually have a lot of shared goals, whether it be heterogeneous silicon, efficient, flexible protocol layers, but all of these things kind of intersect at a natural technology point.
Okay, that was the last talk. We're now open for questions and answers from the audience. Please type your questions into the chat box or into the question and answer tab. I see a question from to Brian to talk more about the latency optimization slide. Not sure if Brian is online. Doesn't look like he's online at the moment. So there's a question to me, this is Elko Bergman, to talk a bit more about the packaging optimization for standard interfaces. So as I showed in the presentation, the idea is the more that we can lock down or agree on the standard interfaces to be used for chip-to-chip communications, the more readily that will support the implementation of design rules, guidelines, even potentially reference designs for that portion of the interface in the package design. So one of the discussions in Jawad's CDX committee is how far can we go in defining those standard interfaces? For example, in an earlier talk, there was a request for flexible pitch on the IOs for the dies, which I think is something that we should be able to support, because we're going to need to be able to route these devices on different types of substrates, such as organic or RDL or silicon interposers. But if we're able to fix pad locations or pad assignments, then at least we can develop some references for the routing between two interfaces that are looking at each other between two dies. So that was the thinking behind that, but we need input from the chip design community on how far we can go with that to see how much we can standardize the interface designs at the package level. I don't see any other questions coming in. Do any of the other speakers online have any comments they'd like to make?
Sure. There was a question from Aaron about low latency rotency. Now, I missed the slide that Brian showed, but we think about it since we have Chiplet as a in our roadmap. So we look at different options, obviously from the physical interface, which is either the parallel or low latency XSR, VSR type SerDes, the protocols, and the low latency FEX as well. So that's at a high level. I'll be happy to expand on any of these areas. On a protocol level, what's been very common in my experience for low latency chip to chip, it has been interlocken. So we are looking at the lowest latency interlocken type of protocol as well. Hope it helped to answer your question, Aaron. We'll be happy to follow up later. Perfect, thanks.